Okay, I think he'll let us.
All right, guys, we're gonna get going in a second.
Oh, perfect.
Oh, it's trying.
Oh, you can. Yeah, perfect.
I don't know how to use Arc, at least
Yeah,
not
no worries.
giving it to you. Okay, sorry for the hold up. This will be the 161 midterm review for memory safety. And, some of these questions in past papers can seem a little daunting, especially the memory safety. But if you just know the principles well enough and you know the project well, and the project is a little bit over the top sometimes. You like think about how long it takes you to do a project question. Like some of those questions took me 5 hours. In the exam, you probably have 20 minutes for a question. So as far as what to expect, if you just know the principles for the memory safety well, the vulnerabilities and how to mitigate them, you should be in a pretty good situation, a pretty good position to do well on that portion of the midterm. So that's sort of what we're going to focus on today. So we are going to do a quick x86 review. The thing that I would say about x86 is that if it comes up in the exam, it's usually like 2 or 3 points, right? It'll be a potpourri question, or it'll maybe be a brief question at the end of a memory safety sort of question asking about what will happen when. But other than that, I don't think it's too important. It is important to know for real life, and especially being on the exam writing team, I know it like the back of my hand because it does inform how you write questions and to ensure that every exploit works. But other than that, I would say that the sort of parts 2 and 3 are more important. And also we want to make sure we spend a lot of time on questions and not just on the lectures. So you can see how we can apply the things that we're going to recapping in today's review session. But yeah, to start off with, let's just get a reminder of what the memory looks like in C. So most of the time we are in the stack, right? This is where most of our, stack smashing attacks and off by one attacks, so on and so forth occur. I'm pretty sure that, and someone, double check me on the ad stand, but I think heap overflow attacks are out of scope for the midterm. Yeah, so we won't worry about the heap, but it's good to know that's where dynamically allocated variables are. And then there's also the static and the code itself, right? And the code, if that's one portion which does come in handy for certain types of vulnerability or safety mitigations, where you can no longer write into the stack, or you can write in the stack, you just can't execute into it. But we'll cover that in a second. So we're going to look at the x86 stack frame. And you guys from the project should know how to draw stack frames. Very briefly, if you have a function, first thing you put onto the, what's the first thing we put onto the stack frame when we have a function? Arguments, right? And is there any particular way we load them onto the stack? Reverse order, right? Exactly. So we will, this is sort of how it's done in x86 notation, but I think that for the purpose of the midterm, the only thing you really need to know is, right, like if we have,
Yeah,
we can see this. What's up?
yeah, we can see it.
Okay, good. Like, not to hate on x86, it's cool and all, but I think, right, if we have arg1, arg2, right, and then, well, let's just simplify it with one argument, and then we have like buffer, right? Some char buffer, 16. How, like, does someone want to give me the first two or three items on the stack frame here? Right, so the first thing we said we do is we put the argument on the stack frame, right? Right, so we'll put arg1 on the stack frame. Then there's two acronyms that go on the stack frame, which I'm sure you guys are kind of sick of at this point. What goes next on the stack frame when we're drawing these stack diagrams? Yeah, RIP, SFP, wonderful, yeah. And then finally, what are we loading on? This is a simplified example, but we're going to put on the variance, right? And I cannot stress how important these stack diagrams are, because, when I write, the memory safety questions for the midterm, like I'm always trying to think about the stack diagram, right? And then how I can exploit that to make an interesting question, right? This is where sort of questions are made or broken in terms of understanding. If you can get the stack diagram down, you can start to realize, okay, there's something interesting here. Like maybe the buffer is one more byte than I'd expect, or maybe this for loop is exploitable some way or another, right? But you have to get the stack diagram correct to even have a chance at correctly answering the question. So review your, the project write-up, but really make sure that you understand the stack diagram. I'll see, this is sort of the calling convention. I will say, because we have limited time, I'm going to try to focus this, tailor this more to what I think is valuable in terms of exams. And, this is important stuff, but I'd like to, my role for the core stuff is to write the exam. So I think when I say, if I say learn the stack diagrams, right? x86 calling convention is important, no doubt. And especially if you, travel lower down the stack, like I'm currently in 151. I think some of you guys are also in East 151. There all of a sudden, knowing, that kind of stuff becomes a lot more important. But for the purposes of the midterm and just doing well in that, know how to draw your stack diagrams, right? Another thing that is important to know is just how sometimes students get confused in how addresses are allocated on stack, right? So if I have let's say we run GDB and we get this. Can someone tell me which of these is the address and which one of these is the value? Left side's the address? Yeah, right. So what this means is at this address, we have this value. And if this was the RIP, then we are overwriting this. And this, the RIP, what does the RIP do again, in layman's terms? Right. So like what's going to happen next, right? And so sometimes these questions can sort of play with these concepts of like what is the address and what is the value stored at it, right? So very important to know the difference between the two, because that's always a trick question we love to throw at you guys. Interesting. So the RIP points, the value of the RIP points to the, well, what's going to happen next, right? Or it like where the instruction pointer is going to return to next, if we want to be more formal about it. The address, so if this is the RIP, the SFP, right? Let's say this is at some address. Does anyone know what the value of the SFP is? Yeah. So the address will usually be that, like in terms of exams. Oh, that's the other thing I should mention is that we, if anyone's taking 164, you guys know that compilers are pretty useful and they've gotten pretty good, right? Especially C compilers. So sometimes things get moved around in real life, but for the purpose of exams, you can expect that everything is drawn like we teach it, right? So RIP, SFP, and then, we'll get to canaries, but those will be right below. Sometimes that isn't always the case in real life. And, if some of you there have been students who have come in office hours and said, hey, I'm looking at GDB. Why is this the opposite order of my stack diagram? Is my stack diagram wrong? No, it's just that the compiler for C is very good. And when it sees a way to more efficiently allocate memory, it will do so, right? And we're actually working on how to turn that off to make sure that it's consistent. But for the, just, in case any of you guys have seen that, it was question 5 in particular, you can always expect the stack diagram to be drawn how you might think it will be. But yes, so the address of the RIP is usually, of the SFP is usually 4 bytes below. But this is something that is a niche fact of the course, but very, very useful, is that the SFP is actually a chain of pointers. So if I have, let's get rid of the RIP for a second and say this is SFP main, and then SFP foo, right? Let's say this is at some address X, then the value of this SFP points to the previous one. And this can come in quite useful if you're like looking for a pointer on the stack, but you don't have one. You always have one in the SFP, and technically also in the RIP. But the RIP, sometimes you don't know where it's going to point to, right? The SFP of foo, you know, always is going to point to the SFP above it. That's one of those facts. There's 2 facts I always like to say. It's that and the fact that when we get to canaries, we'll talk about it in a second, but the value of a canary in different stack frames is actually the same. All right, sorry, let's go on. So this is the calling convention. I will say it's the beautiful thing and very, very fond of it, but it's not too crucial to, well, there'll be probably be, some questions on the calling convention, but just know it at a higher level. What I mean by that is, in particular, is this segmentation between blue and green. So if main is calling foo, main is known as the caller, right? And foo is the callee. And what the blue portions of this is done by the caller. And then at the green, when the sort of execution command, so to speak, is passed over to the callee, then that's what the callee will take care of steps 4 through 10. And this is important because in certain classes of attack, like a ret to ret or a ret to libc, or any way where you hijack the traditional calling convention, because we skip these first 3 steps, sometimes it's a little messed up, right? And that's like, in a sort of what happens like in a kind of also in an off by 1 attack, how like you put the SFP somewhere, the RIP will talk 4 bytes about it. Or especially if you looked at one of the harder attacks like a ret to libc, where you have to space those 4 bytes in between. That's sort of a more advanced attack, but understanding just what is done by what, and in particular what's happening in this divide, is quite useful, right? But I don't want to say that this is not useful, and without like speaking directly in the exam, it's always tested in some capacity. But if the exam is tomorrow, you really want to focus on how to do well in it. I would say spend your time more on learning the memory safety vulnerabilities, and then also how each vulnerability can be patched. And that's what we'll move on to. So I won't spend too much time on the calling convention. If you have time and you feel confident, by all means learn it. It'll come in useful. But otherwise, I would say let's focus more on the calling convention or on the actual exploit. So this is kind of how you see, especially this segment is quite salient, right? That's the SFP is pushed onto the stack by the callee, whereas the RIP is pushed on by the caller. That is quite important. But otherwise, I don't want to say that you shouldn't learn this. I don't want you guys walking out of here saying, oh, I don't need calling convention. And then you open the exam tomorrow, which I wrote, and say, oh, there's something on calling convention. I'm just saying, I want to clarify that, like, as far as most efficient way to get a good score in this exam, let's focus on sections 2 and 3. So I'm going to skip through this slightly. And then we'll also look, the calling convention is sometimes useful in particular to certain experts. So like for ret to ret, when we cover that, we'll look at, okay, how does this mess up the calling convention? And how sort of does that impact where stuff is stored, or like where the pointers go? But right, so let's start looking at the classes of attacks. So does anyone guess what the first one is that we're going to cover? Like, what's the bread and butter of 161 memory safety attacks? Right, canonical buffer overflow. So this is where a lot of attacks actually sort of default back to this, right? Where we basically are allowed to write more than we should, right? An off by one attack, technically a separate attack in this class, but you can think of it the same principle. We're allowed to write one more bytes than we should. But at its simplest, the goal of most of these exploits is to overwrite the RIP. Because if we can get to the RIP, we can tell the program where to get next. The value of the RIP, I should say, right? Remember this distinction that I said earlier, it's always very important to differentiate between the value and the address of the RIP. So the goal of most memory safety attacks is to overwrite the value of the RIP, because then we can tell the program where to go next. So someone could overwrite the RIP of the lights, and told them to turn off. But otherwise we can, and most of the time we're trying to execute shellcode or some address, right? Like if we can rewrite the address of the RIP to, I think that over there, yeah, I think so. Very cool. Oh, whatever. Then we can tell the program where to go. So usually in a stack smashing attack, there is some function which doesn't properly check the bounds. Or if you it's all the exams I wrote over the summer, then you'll see that sometimes there's a for loop that will let you sort of copy bytes where you shouldn't be able to access the memory usually. And the way that this works is that one way or another, we are trying to overwrite the RIP and turn it into the address of shellcode or point to somewhere where shellcode is. And this is a second important point, right? So first we have to overwrite the RIP. But the second question is, where can we put shellcode, right? So best case, you can put it, below and point it to that. Remember, sometimes in the project, you can put the shellcode above and just point the RIP 4 bytes above itself. That sometimes is an art within of itself, is trying to figure out, okay, even if you have like unlimited write access, where can I actually put the shellcode that this will work? And like the way that most of these questions are structured is like we keep throwing these hurdles at you that make this canonical buffer overflow harder, and you guys have to find a way to jump over them. So now we get onto the second attack, and this is the integer conversion attack, right? This is where we have the disparity between signed and unsigned data types. Does someone want to like briefly explain like what can an unsigned integer do, or what can a signed integer do what values can a signed integer hold that an unsigned can't? Yeah? Right. And this is we sort of teach these, but back in in the early days of CS, these were like real problems that people didn't think about, and then served to like provided serious memory safety vulnerabilities to critical infrastructure. And the way that at a high level that integer conversion attacks work is that, let's say we're smart, we managed to patch this buffer overflow by saying, okay, we're not going to let what you write into the buffer be more than 256 bytes or more than 128 bytes, right? But the issue is we used a signed integer, whereas this will also be included in your appendix, but most functions that take in a size requirement like fread is a size t, it's an unsigned integer. So what this means is we can set, when we have this pass, like this if statement, right? And let's say it's like, code aside, let's say it's like we want to say it's less than 128. If we set it to -1 or something, that will definitely pass the check. But that's because it's being cast as an unsigned integer. If you guys recall from 161C, it's 2's complement, right? 2's complement. That will then be cast when it's just treated as an unsigned integer. So these negative values are not a possibility. That will then be cast to a very large positive number. As you remember from question 3 of the project, I think. Right? Two? Question 2,
Yeah.
right, yeah. So that is integer conversion tax at a high level, right? The next one is the off by 1 attack. This is another example where we had a canonical buffer overflow, but we have limited it somehow, right? Oh, I think it's because you hit this, or you lean against this. Oh. Wow. So we want to stop users from being able to write unlimited. So we put some kind of limit in, but we just messed up slightly and we gave them one too many bytes than we should. So what this usually means is that you can overwrite, what can you usually overwrite an off by 1 attack? What in particular, the SFP? The least significant byte. So, and if we recall, if we point the SFP somewhere, like other than its current location, like other than this, so we change the value of the SFP by the least significant bytes, and we point it somewhere. Where will the RIP go after, like, you know, once the function epilogue continues? Yeah, so the RIP without loss of generality will pop 4 bytes above that in these kinds of questions. So sometimes you can't overwrite the SFP, or you can't overwrite the RIP, but you can change the last significant byte of the SFP. So you're like, okay, I'm going to try point the SFP into my buffer, and then I'm going to put my shell code into my buffer. But hold on, I can't just put it at the bottom of the buffer because I have to realize that because of the function epilogue, and because of what the callee and the caller does, and more importantly, what the green portion, right, what the caller expects to already have been done, namely that the RIP has already been pushed onto the stack, we have to account for that fact, and then we'll add 4 bytes of padding because we know that the program will think that the RIP will be 4 bytes above that, right? So that is the general principle of the SFP attack. So the interesting questions that we can ask about off by 1 attacks is to do with sort of the range of it, right? Namely that if I have because if we have a buffer at, let me give an example actually, right? This is something that we asked over the summer, right? If I have a buffer that is FF, DB 00, right? Or something, what does my SFP have to be in order for me to be able to point to this, right? Because we can only change the least significant byte of so let's just say the SFP is 4 bytes. Which of these bytes have to match in order for this to work? First 3, right? If these aren't the same, right? If this was FF, and then for some reason DC, no matter what we change the least significant byte of the SFP to be, we can never get to the buffer, right? But sometimes the buffer can be, it can have a large range. So maybe it starts at DB90, but then eventually it's a large buffer, so it gets to DC, right? These are just like some more ways that we can make these questions more interesting. But they just think about the principle, right? Everything, always try to boil it down sort of to first principles and try to understand, okay, this is an off by 1 attack. Would this still work here? Like what conditions have to be true in order for this to work? So this is sort of what happens visually. And this is, where you can actually look at what the individual EBP and ESP do in the exam. But broadly, you just have to remember that the RIP will pop 4 bytes above where the SFP is plotted. Yeah, question?
Why is so much overwriting with RIP? Like, is overwriting RIP usually much more powerful than overwriting?
Honestly, not really. I think it's just, it's easier, right? If you overwrite the RIP, we're literally telling the instruction pointer where to go next, right? It's one step. When we overwrite other things, or like we do a red-to-red attack, and that's usually because we don't have that easiest option available to us. So instead, we're going to try overwrite the SFP in hopes, well, not in hopes, in knowing that the RIP will be somewhere else. So we're still getting the RIP to go somewhere, but instead we have to do it through the SFP. And the important thing to understand is there is a distinction between whether the RIP treats stuff as an address or as instruction, right? Because usually when we overwrite the RIP, it treats that as an address, right? It's saying this is where we should go next. But in off by one attacks, if we place if we get the SFP to point here and the RIP pops 4 bytes above it, and we put shellcode right there, we are executing the instructions itself of shellcode. So this is actually a third thing I want to add. So there's 2 things I said at the beginning. A third one is that sometimes trips up students is understand whether these important pointers, namely the SFP and especially the RIP, are they going to treat something as an address or are they going to treat stuff as an instruction, right? Because with our canonical buffer overflow, we are changing the RIP to an address of the shellcode. But in other attacks, we're going to point the RIP to the shellcode itself, and then it will start, because the ultimate goal is, the reason, if you recall from lecture, this is out of scope, but the shellcode, it's called shellcode because the most powerful thing you can do to sort of hack into someone else's computer is to get terminal access, right? Some open some shell, that's why it's called shellcode. So, but to do that, we have to execute some instructions. So remember that the shellcode is byte instructions that will do a certain task for us, which has been abstracted away for this course. But, if you want to sort of tie it to a real world example, it's usually done because we want to open a shell, right? So remember that distinction. And I am sort of running over here. So now let's talk about the ret-to-ret attack, right? So this is where instead of directing to a specific memory address, we can take advantage of a ret instruction and the presence of a pointer that can redirect to the shellcode dynamically. So usually, when do we want to use a ret-to-ret attack? Yeah?
When ASLR is enabled.
Right, because what does ASLR do to addresses? Right, so, these usual attacks where we overwrite the value of the RIP, unless we can sort of dynamically get the value of the RIP through a printf statements, those don't work anymore. So we have to use, because even though, I guess this is sort of part of the next part of the slideshow, but even though ASLR changes the addresses themselves, it does not change the relative distances of, how each of the 4 components of memory are allocated within themselves. So if you know that the buffer is 8 bytes below the RIP, no matter how the addresses are randomized, that will always still be the case. So we sort of, it's like, okay, we've been stripped of our ability to put it to specific addresses. Let's abstract that away and work in sort of a relative sense, where we instead try to use what we know about how the memory is laid out to try and get an attack to work. So what does a ret instruction actually do? Like in, either in terms of the function epilogue or just in sort of layman's terms. It's just like a pop EIP instruction, right? So what this allows us to do is that when we have this ret instruction, we can take the value of the address pointed to by the ESP and load it into the EIP, and then the value of the ESP will increase by 4. And why does this matter? This matters because we know that whatever we place when we pop EIP, when we execute this ret instruction, we pop the EIP, right? So that tells us something about the RIP and how we can use that. So if we look at this diagram, we can set the RIP to an address of a ret instruction. So let's say, for whatever reason, we can't point it to the shellcode directly because the shellcode is just known as an address and that's been randomized. But we know, like we had in the project, that a ret instruction is always like a certain number of bytes above or below the RIP. So we can try to set the RIP to ret instruction. So then when the function returns by the calling convention, we then move the ESP and the EBP, which will assign or set the value of the ESP to the EBP, right? And now we can run pop EIP. So that's where we sort of pop the EIP off the stack. And this will load the value of the RIP into the EIP, which is now the ret instruction, and then our ESP increases by 4 bytes. And because our EIP points to the ret instruction, we can run this once more. And then this is sort of where you have it like certain questions will use different numbers of ret instructions. Sometimes you have like a ret sled or like a no-op sled, right? You have a ret instruction and point it to somewhere. And then you need to have these. Does someone know what does a no-op instruction do? Yeah.
Goes to the next super, little bit.
Yeah. No operation, right? Basically what it does is it moves the instruction pointer up without actually like executing anything. So that's a very useful task. If like we have something useful up here, but our pointers down here, how can we get it here? Just if we can, fill it with no ops, right? And then now because our EIP pops points to the red instruction, we can run this, right? And the ESP is then pointing to a pointer right now, and we can load this value into the EIP. So then if all of this goes to plan, we hope that this pointer will land us somewhere inside of the buffer. And then we can maybe be able to control the buffer. And then like this is where we have the no-op instructions, where we basically try to, so let's say we have this red instruction and we can get the EIP kind of close. We can use these no-op instructions to move the instruction pointer up until we have our shell. And right, importantly, this is a byte, this is an address, or these instruction bytes? They're bytes of instruction, right? So we'll just start executing this. Keep going 15. Yeah. Okay. So I know that the red, I sort of said, don't worry about the function epilogue, but the easiest way to, I think, learn the right instruction is just to do a couple of class questions, because when I was a student personally, maybe you guys are better at this than I was, which might be the case because I didn't actually have 61C when I took the class, but hurt a lot. But or if anyone hasn't got 61C, this is maybe a sign that you can do it as well. But either way, I'm digressing. I always found these very confusing, the red thread attacks. They definitely are the hardest part of the course. But a way to learn them, I think, is if you just do if you look at most question papers, they won't really deal too much with the action function. Some of them will, and those are annoying. But for the most part, if you just want to know how a red thread, just do a couple of the class questions, look at the discussion, and if you just have a general sense of how everything works, and in particular, if you just know what the EIP is doing, right? If you know what the EVP and the ESP are doing are great, but the EIP is, is our Hail Mary when it comes to sort of like these attacks, right? We're trying to get the EIP to our shellcode. That's always the end goal. So if you just know how the EIP works and sort of what the red instructions do and how it can circumvent ASLR, which we'll get to in a second, then I think in terms of red to red attacks, you've got your bases covered pretty well. So now let's begin to look at classes of defenses, right? So when we had this buffer overflow, the issue was that the intruder could just write up on the stack unperturbed, right? So the first way we can stop that is through stack canaries. And what stack canaries are, and this is, does anyone know what a stack canary is and like where this word, this term sort of come from? Yeah. Right, exactly, right. So back in the day, when maybe I wouldn't have been a TA, I would have been working in the coal mines instead. And the issue with that is that when I'm down in the coal mines, there's a lot of dangerous gases that could harm me or kill me. So what would happen back in the day is that they would bring these canaries down. Unfortunately, these would be sacrificial animals. So if the canary would pass out or pass away, then this would be a sign that something was up, right? That there was a deadly gas leakage or something. But in our case, we are fortunately not sacrificing an animal, and instead we're just sacrificing 4 bytes. So what a stack canary is that usually right on the SFP, and I say usually, this is different architecture to architecture, but abstract, like for the purpose of this course, you can always assume that, and especially for the purposes of the exam, you can always assume the stack canary is right below the SFP. And what happens is that at compilation, the CPU will check, is this value of the stack canary the same as what it was before? So if we just stack smash the attack and replace everything with garbage until the IRP, we're going to overwrite the SFP. Oh, well, we're going to overwrite the SFP, but more importantly, we're going to overwrite the stack canary. And then the issue is that because we've overwritten the stack canary, the CPU will catch this and it will panic out the program, right? So exploits will not work. And this is the interesting fact that I wanted to tell people before, is that if you have main and foo, they both have stack canaries, right? Under each SFP, those are actually the same value, right? This is sort of I'd like to think a niche part of the course, that is sometimes really useful because, you know, you might not be able to get the value of one, but might be able to get the value of the other. And by getting the value of one, you have the value of the other because they are the same value across different stacks. And the important thing about stack canary is that they change their value every run of the program. So you can't just run the program once, write down the stack canary, and then run the program again and replace the value. So yeah. Now we move on to, I actually want to quickly cover pointer authentication, right? Because this is kind of the same principle. And this is especially salient in 64 bits because eventually, you know, sometime, I think around the turn of the century, maybe a little bit more, we decided that 32-bit was not enough, that we needed more memory space. So the natural thing is to do is move up a power of 2, and now we're at 64 bits. But the funny thing about 64-bit is that I don't actually know the exact number. I learned it when I was in over the summer. It was in one of the lecture slides, but the address space of 64-bit is so large that I think it's larger than all the total storage that we have as humanity. Like, it's some exorbitantly large number. So what this means to say is that we don't actually need all 64 bits to represent addresses. So in practice, we use the first 48 bits to tell, like, just as we would in 32-bit to like tell the program what to do. And then the last 16 bits, you can think of this kind of as a stack canary. If the stack canary in the SFP had like a baby, then we have the sacrificial value at the end of, or all pointers actually, all pointers. And this is out of the scope of the class, but if you're interested, this actually feeds in neatly with the cryptography part of the course, because what's cool about pointer authentication codes is that every pointer has a unique authentication code. And that is to do with, it's like an integrity check, right? That's appended onto the end of the pointer. And this is the same thing, right? It's just a little bit more powerful because let's say for some reason we were able to hop over the canary and overwrite the value of the RIP. Pointer authentication codes are on the RIP. So if we overwrite the value of the RIP, we're going to overwrite the value of the authentication code, and the same thing happens. It panics and doesn't work. So yeah, those are PACs. Kind of similar in principle, just like how they're implemented is slightly different. So now we'll get into ASLR. I kind of touched on this earlier, but this is where we randomize the addresses. So a lot of attacks in this class, we need to know, like, we're given the address of the where we put our shellcode or where our shellcode is, and we just overwrite the value of the RIP to that. ASLR completely kneecaps that because now all of a sudden we can't, you know, we don't know. The shellcode might be at this address in one time, but the next run of the program, we might have completely moved stuff around. And then all of a sudden we don't know where our shellcode is anymore, and we might be pointing to empty space. So this is a pretty powerful, safety mitigation, but it is still exploitable. Most of these are still exploitable, right? One obvious way is that we're able to leak the value of the RIP, right? If every time we can leak the value of the RIP through a printf statement, for example, then we can just put the shellcode right above the RIP and we say address +4, right? We just overwrite the value of the RIP to address +4. Because of what I said earlier, the relative distances between how variables are or how stuff is stored on the stack does not change. It's just the address of it. So all of it gets shifted down. All of it gets shifted up, right? But the relative distance does not change. So now we move on to, oh yeah, I should say also like return-oriented program, like ROP attacks, red attacks, like as we saw earlier, those are sort of, and I think maybe they're in some of the problems that we'll get to in a second. Those are quite useful for circumventing ASLR. So now final class is non-executable pages. So eventually someone realized that, you know, hold on a second, why would I let people both execute and write in places of the memory, right? Because let's say we have the code, right? It makes sense that we can, you know, that we can execute the code because, you know, like if I have a Python program or a C program, I'm going to want to be able to execute the code. But that shouldn't be writable. And in turn, the stack, the heap, and the static, those should be writable because that's how our whole function epilogue works. Like we're pushing and like we're moving things on and off the stack as the function epilogue continues. So those obviously should be writable because we want to be able to, you know, put the value of the RIP on the stack, or put the value of the EIP onto the stack as the RIP. But should those necessarily be executable? And the answer is no, right? It's an obvious safety vulnerability. So that is where this sort of disparity was introduced, where the static, the heap, and the stack are writable but non-executable. So what that means in principle is that any usual attack where you try to like overwrite the stack, you can't execute that, right? You cannot put your shellcode into the stack and execute it because it is marked as non-executable. So the way around that is to find something that is executable, and this is usually where we have these ret to libc attacks, which we might go into detail later, but much about that. Pointer authentication we covered. Okay, so these are now the main takeaways before I hand over to the best tutor in the course. Writing safe C code is pretty good, right? We've shown that. And if if any of you guys have patched that together, but if you look at project one, what the passwords, how each question had a password, if you put each of those passwords together, it spells a nice little message from the core staff, which more or less says, don't use C, use Golang instead, right? I don't know the exact wording of it, but writing C is difficult. And we've shown that by all these vulnerabilities that are present in C code. But despite this, C is still a very popular language. And it's also a pretty old language, so people have had time to deal with these issues. So we've shown that there's many ways to patch a lot of these vulnerabilities, but each of these mitigations by themselves is usually not powerful enough to completely like stymie a memory safety attack. So if you look at past papers, one thing we always like, we'll give you an exploit, and then we say like, would this still be possible with non-X, right? And then you have to think like, okay, the question is asking me, could this still be possible with non-executable pages? Let me remember what non-executable pages does, what does it make harder, and what is still possible with it. So that's some questions will have a memory safety mitigation installed in it by default, but usually, if you look at past papers, it's very common to be asked, would this still be possible with this enabled or with this turned off, right? So just remember the key principles of each memory safety mitigation, what it makes harder and what is still possible because of it. So now we are going to work through question one, and I'm sorry that we don't have worksheets for you guys. Does everyone have a means to look at the question? Otherwise, we could maybe run over and get you guys sheets. I'm not sure if they've been printed is the other issue. Yeah, we'll keep the question up. I will hand over to Nazar, and he'll take it from here.
Yeah, so let's jump in straight into the questions. So question one is called returnless. And as you can see, it's from like one of our past papers. Probably I'll do like a quick rundown of what the function does, and then I'm gonna give you guys a couple minutes to think about it. But what it does on the high level is we have our function main, and we initialize int variable I, array of characters input, and array of like integer stored numbers. Then we have our for loop where we iterate from 0 to 4, where we set I from 0 to 4 and increment it. We do a printf statement, enter a stored number for like 0, 1, 2, 3, 4 respectively, and then we do a getAs call on the input. And then we store the ATOI. ATOI is a function that converts from string to an integer in C into the stored numbers array at the index I. After that, we're going to do a while loop while I is greater or equal to 0. We're going to print which stored number do you want to print. We're going to do, again, getAs on the input. We're going to convert from string to an integer, that input that we have gotten. And if I is greater or equal to 0, yes. Well, then we're printing it out. And after that, we return 0. So first question is, assume the program is paused immediately after executing line 4. Complete the stack diagram below. And I'll probably give you guys like 2 minutes to think on it. Oh, by the way, and probably one important fact is we have stack canaries enabled. All right, let's jump in. So it should be pretty straightforward, but does anybody want to tell me what stack diagram they got? Yeah,
Main,
rip of main, yes,
then, SFP, then stack canary,
correct.
I input stored nubs.
Yes, perfect. So remember from the calling convention, we always put RIP and SFP. Whenever you see SFP, RIP is right above it. Then recall that since stack canaries are enabled, they're going to be right below it. And stack variables, I input stored numbers, they're pushed in order of declaration. Okay, so question 1.2. Which of the following vulnerabilities is present in this code? I'll probably give you guys around like a minute and a half to think about it. And I'll probably show the question. All right, so time's up. Does anybody want to tell me what type of vulnerability is present in this code? Yes? Yes, that's perfect. Buffer overflow. Why? I mean, whenever there's like a getAs function, there's always some sort of like buffer overflow involved. So if you see a getAs function, it's pretty safe to assume like most of the time that it would be a buffer overflow attack. Specifically, yeah, getAs like just doesn't ever check the length of the buffer. On the other hand, fgetAs is a different story. But since we have gets here, it's going to be buffer overflow. And one note to say here is that there are no format string vulnerabilities. Even though we have printf statements over there where we print out like %s and everything else, there are no format string vulnerabilities for this specifically case. We can still use printf statements for our reasons, but we cannot overwrite RIP with printf. So that's why it's not going to be a format string vulnerability, but it's going to be a buffer overflow vulnerability. No integer overflow vulnerabilities, obviously, because there's not really any place where integers are used over there. And there's no signed unsigned vulnerabilities because we never cast a signed integer onto unsigned one. Okay, so for next question, Which of these inputs to the getS call at line 14 will leak the value of the canary? And the options are a string of -1, a string of 9, as a string of like hex byte of 00, the string of 12, or like none of the above. I will put the question back on, but just be aware that these are your options. And I'll give you guys 2 minutes to think about it. All right, so time's up. Does anybody want to try to attempt what input to the line 14 causes the leak of the value of the canary? No worries. This is a 4-point question, so I do realize that 2 minutes is like not enough. But for the sake of the time, we can probably just I could leak you guys the answer, and it's going to be the solution 9. Why is that the case? Remember from our stack diagram that we want to leak the value of the stack canary. Stack canary is located right above the local variables. Remember that we have integer I, we have 16 bytes of the, I think, character array input, and then we have also an array of 4 integers, which is also 16 bytes. The main vulnerability comes from, in this while loop, in this case, it's going to be, we're providing the input into the getS call, then we're converting the whatever we have received into an integer. In this case, the one is going to be 9. And then notice that on line, I think 17, we're printing the stored numbers at location I. So we don't check what we are passing in there, but we're accessing the array stored numbers. And we can do that. There's no bound check. As long as I is greater or equal to 0, it's going to work. So what happens when we set the I equal to 9? I equal to 9, I guess I could like quickly write out the this the stack, we have stored nums. We have input, and we have I. This is 4 bytes. This is 16 bytes, and this is 16 bytes. And here we have our canary. Oh my God. Sorry about that. So now when we're trying to access stored nums at index 9, what's gonna happen is we're gonna skip this block. We're gonna skip this block of code. We're gonna skip those 4 bytes, and then we're gonna print out our canary. And that's how we leak the canary. Does anybody have any questions regarding to that? Why is it 9 and not anything else? Doing good? All right.
Actually, I knew.
Yeah.
Why do we skip, why were we able to skip 16 bytes if we're saying, like, my assumption was I gets like an individual byte,
Yes.
but if you have 16 bytes of stored nums and then 16 bytes of input and then 4 bytes of I, 4 bytes of canary, how does 9 just skip all of that and skip 36 word amount of bytes?
Right, that's a great question. The reason lies because our stored numbers array is initialized as integer. So when we do pointer arithmetics on integer, notice that this is an array of integers, not an array of characters. Characters are 1 byte aligned. So like we're going like 1 byte. When we're accessing integers, on the other hand, each hop is going to be 4 bytes wide. That's why we're able to skip over entire blocks of 4 bytes. And that's why I equals 9 would be plausible over here. Does that answer your question? Okay. Yeah, and here's just another explanation. So the canary must be stored at index 9, 3, indexes 0 through 3 are stored numbers, 4 through 7 are input, and 8 is I. Yeah, and everything else is just what I've described right now. Okay, so now moving on to question 1.4. So assume that the address of our input is 0x7ffc9180. Fill in the blanks to construct another input to the getS call at line 14 that will override the canary with itself and cause the program to execute the malicious shellcode. And also write your answer like in the Python in syntax, right? Like we did previously in the project 1. You can also use the variable canary as the leaked 4-byte canary value that we have determined from the previous part, and the variable shellcode as the 32-byte shellcode. Yeah, so for this one, this is a bigger question, so I'll give you guys 3 minutes to think about it. All right, does anybody want to try to attempt this question? Maybe even if you guys got like even like one part. Yeah. Yeah.
I think I messed up on like everything else. I also thought that the D is multiplied by 4, so overwrite the. Oh, wait. Actually, I might have actually, one of them was 4, it should overwrite SFP.
Yeah, we have like, well, do you mean with regards to this? Like, yeah. No, I think you're definitely like on a good way. I mean, especially like since Canary is right below the SFP. So I think that your reasoning is definitely like good. How about like other blanks? Yes?
Well, I wrote 20 bytes of garbage using the A to
Yeah.
get us up to the canary. And then for the address there, I couldn't quite calculate the last byte. You have to move it slightly above input, but it was.
Right. Yeah, for sure. Sounds good. And does anybody want to know what to put like into these two? Yeah.
-1 so that the while loop doesn't run.
Yeah, perfect, exactly. And how about like the X byte? Null terminator. Yes, perfect. Yeah, and did anybody get like this address at the end? Perfect. Yes, perfect. I think we got all the parts. So the first part, as you have pointed out correctly, like this, like at this point is just like pattern matching, right? We have like values canary and shellcode available to us. So what we're gonna do is we're gonna just fill in like those like two values. So this is completely correct. -1 to exit out of the loop. Yeah, and let's just like think like through this exploit like one by one so that everybody's like on the same page. So at line 15, we call the string conversion to the integer on our input. So what does it do is it takes a string and converts it to the integer, right? So that's why we need -1 and null byte terminator. Here's a little bit like more of a like deeper like explanation why. Because we don't want to like because we want the while loop that just to exit out. We have the while loop check like while I is greater or equal to 0. That's why -1 comes into the place. But we also want this to be a string. So that's why we have to put the null byte terminator. Now what this is gonna do is it's gonna ATOI is gonna take the input and it's gonna take the -1 and it's gonna convert it to an integer and assign it to I. That's how we break out of the loop. Now, as one of the students put it out, just like pattern matching from this point, right? We have like two values. We can just put, we have canary and shellcode. So where do they go? Probably over there. And we have to put canary first and shellcode right above the RIP. So now we know that this like XXX, this is probably going to be like our new RIP. And then B is the bytes of garbage that are overriding the SFP of main. So what we're gonna do? Oh, first we didn't figure out why the A, what goes into the A. Notice that we put -1 and the null byte terminator into the input already. The calculation is absolutely correct that it's 20 bytes from the input into the canary, but we have already filled it out with like 3 bytes, minus sign, 1, and the null byte. So 3 of them are taken. So we have to add 17 more bytes to fill out everything up until the canary. That's where the 17 comes from. And then we know that we have to overwrite SFP and the RIP. So what's going to be the SFP? It's going to be 4 bytes. We're overriding it with garbage. And how do we calculate our RIP? What we do is we know the address of the input, and we know that it's 16 bytes. Then above it is 4 bytes of canary, 4 bytes of SFP, 4 bytes of RIP, and then we're into the shellcode. So what we're going to do is we're going to take the address of the input, add 16 plus 4 plus 4 plus 4 plus 4. I think, what is it, 32. And we're going to just override it with the address of input plus 32. So if the address is 0x7ffc 9180 plus 32, 32 is 20 in hex. So it's going to be 9180, I think. Yeah. Yep. And this is the whole like exploit. I know this is like a little bit confusing, but does anybody have any questions? Yes. Can you repeat that question? Yeah, 17 we get is because recall that this is all one get s call. So we're trying to fill the input. So when we try, we're sending the whole entire payload into the input. So first we send -1. So -1 is gonna take the space in the input. So it's gonna be 1 byte of minus, then 1, and then null byte terminator. So 3 bytes are already taken. Then notice that from the beginning of input to the canary, we have 20 bytes total that we need to overwrite with some garbage. So if those 3 bytes are already taken by -1 and the null byte terminator, that's how we get 8 times 17. Because we're just like filling everything up until the canary. And then we want to overwrite the canary with the canary, if that makes any sense. Does it make sense? Okay. Yeah, another question?
null byte terminator stops the ATOI, and then the new one at the end is what stops again.
Exactly.
Do you know a lot about how ATOI works?
No, it's going to be provided on the reference sheet if there is any, if it's ever there. Yeah. Any other questions? All right, good. So now we're gonna skip question 2 because it's a heap overflow vulnerability and it's not in scope. So let's jump straight into question 3. Now, this is the question on the probability. It's probability of man-bad. So consider the following vulnerable C code. We have unsafe function, which allocates 8 bytes on the stack to the buffer. And then we're performing a get-s call on buffer. Very nice. And then we have our main function where we call the unsafe function, and then we just return 0. Assume that there is no compiler padding or additional saved registers in all subparts. Also assume that the shellcode represents 8-byte shellcode, only 8 bytes. And you run this code into the GDB once and discover that the address of buffer is located at the address 3A9D2800. So the question is, first, suppose that there are no memory safety defenses enabled. Which of the following exploits would cause shellcode to execute? And you should select all that apply. So I'll give you guys like a minute and a half to think about it, and then we can recoup. Yeah. Yes. Recording. All right, does anybody want to try to attempt this question? Yes? You said all three? Yes, that would be absolutely correct. Do you mind telling us why? Mm-hmm.
Is where the address was pointing. For the second one, it was the shell code at buffer, but then the address also accommodates for that. And then for the last one, it puts it for above the buffer and the address is also.
Yes, exactly. So just to recap, first, it's completely correct, all of the above. First option, what it does, it puts the shellcode above the RIP. And we are overriding the RIP with the correct address that is like RIP plus 4. So first one is correct. Second one, we are putting shellcode right at the beginning of the buffer. And notice that one of important thing is that shellcode is only 8 bytes. That's why it just so conveniently works out that shellcode takes the entire buffer and nothing else has been overflown. So that's why, and also our RIP accommodates for this change. So this will also be a valid exploit. And then last one, it's a little bit a trickier one because we are first inputting like 4 bytes of garbage, and then we are putting the shellcode. Notice that this is gonna overwrite second half of the buffer and the SFP of, I wanna say main. Actually, I think it's unsafe function. And then because it's only overrides the second half of the buff and SFP and it doesn't touch the RIP, we're good to go. And also like since RIP just accounts for this 4 byte shift, it should be, it's gonna work out just well. So now for the next question. For the rest of the question, if ASLR is enabled, each segment of memory is exactly 0x10000 bytes long. And each starting address always has 0000 as the lower or like least significant bits and has 16 random upper or like most significant bytes. For example, the stack segment might be located between addresses that you see like below, like 0x389D0000 to 3A9E0000. But it will not be located between addresses 3A9D0100 because we said that they're gonna exactly be ending in 4 zeros. Yeah, just like because they're not gonna be, the bottom 16 bits must always be 0. With ASLR enabled, you run the program in GDB 3 times and print the address of buffer each time. You see the following addresses: 0xEF06 2800, 0x2AEC2800, and 0x910702800. Now, suppose that ASLR is enabled and no other memory safety defenses are enabled. Consider the following exploit. 8 times 12, 12 bytes of garbage plus the RIP plus shellcode, RIP plus 4. What is the approximate probability that the above exploit will work on any given execution of the program? And note that all the the previous part is saying is that the bottom 16 bits are gonna be 0. Yeah. So I'm gonna give you guys 2 minutes to think about it, and then we can recoup. All right, does anybody want to try and solve this question? Or does anybody have an answer to this question? Yes? Is your answer 1 over 2 to the power of 16? Yeah, that would be correct. And the reason it is 1 over 2 to the power of 16 is note that from previous part, we already noticed that this is a valid shellcode, like payload to execute this shellcode. So what we only need to do is we want to ensure that the most significant bits start with 3A9D. So this is going to be upper 16 bytes, 16 bits, and we want all of them to be like the corresponding bits. So our overall, the probability that we're going to get it is the probability of there appearing like randomly 3A9D like in the most significant bytes, in the most significant bytes, and everything else is a valid exploit. So that's why it's 1 over 2 to the 16. Does anybody have any questions? All right. Moving on to the next question. Suppose that ASLR and stack canaries are enabled and no other memory safety defenses are enabled. Assume that the stack canary is 4 completely random bytes and there's no null byte. Consider this, the following exploit: 16 bytes of garbage, the new RIP that starts with X14, and the shellcode. What is the approximate probability that the above exploit will work on any given execution of the program? I'm going to give you guys again 2 minutes to think about it. All right. Does anybody want to try to attempt this question? Yes?
Is saying that we're going to override a canary like A, and the probability of doing that is 2 to the 32. And then in the previous part, we already found that probability of the address of the shell code being that particular address is 2 to the 16. So it's just 1 over 2 to the 16 plus, times 2 to the 32. Yeah, so it's 1 over 2 to the 48.
Completely correct. Yes. So as Cecilia mentioned, the probability is going to be 1 over 2 to the 48. And this is because, take a note of this stack diagram. So we have 8 bytes of buffer. Yeah, something else probably. Yeah. And then we're overriding the canary, 4 bytes of the canary. Then we're overriding SFP, we're overriding RIP to be RIP plus 4, and then we're overriding the shellcode. So the probability that this exploit will succeed is from the previous part, we have found that it's going to be 1 over 2 to the 16, like without any canary. But in the case that the canary just so conveniently like turns out to be AAAA, which requires there to be like 4 bytes or like 32 bits of being 1-to-1 being equal to AAAA, this exploit will work. Therefore, the overall probability that this is going to happen is 1 over 2 to the 32 times 1 over 2 to the 16, which is going to be 1 over 2 to the 48. So yeah, like something that I should probably also note is that from the previous part, why do we only need to care about the most significant bytes? And maybe like one piece of information that helped us figure it out is that we have printed out the addresses 0xEF62800, to AEC 2800, etc. Notice that they're ending in 2800. That means that the stack starts from like the buffer like has to start from 2800. That's why we only care about the most significant bytes to be overridden with like to be very conveniently probable equally to 3A9D. And this comes into play over here because 16 bits of entropy from ASLR from the previous part and 32 bits of canary. Yes, a question?
Yeah, regarding the previous one,
Yeah.
the 3.3, the 3.2.
Yeah.
Here, does that matter that in our exploit we say x10 instead of because it's 2800.
Yes.
But here we're using x10 and x28.
Yes, that's a great question. The reason we're using x10 works is recall that in the stack, our stack diagram, when there is like no canaries enabled, we want to override RIP with RIP plus 4. We want to point into the shellcode over here. So notice that SFP is 4 bytes, RIP is 4 bytes, and then we have our shellcode. Since the buffer least significant bytes start with 2800, the RIP plus 4, or like the address like of the instruction that we want to point to is going to be 8 plus 4 plus 4 bytes above, which is going to be 16, right? So this is where it comes from. 16 in hex is 10. And that's why we are overriding x10 is the only probably like least significant byte that will work. Yes, another question?
So this is only in this particular case because they give us like an example of the GDB output and then the last 2 bytes just like conveniently being the same, and we're like basically they want us to assume that like the last 2 bytes are always going to be the same, right?
Yes, pretty much.
It's not always the case. It's not always.
Yes, absolutely correct. It's not always the case. The whole like premise, like why it works, is because we assume that all this segments, they end in like 4 zeros, right? So say, for example, if this is our like memory layout and we have like, for example, stack located over here, what it says is that it's gonna start at 1000, for example, and it's gonna end in 2000, and it's guaranteed. What the leak of the following addresses gives us is the relative address of the memory location of like RIP with respect to the stack, right? So since we know that the 280, it always, oh, not the RIP, the buffer, right? So we know that buffer always is located at the somewhere like that ends with 2800. And only like in this case will honestly this will ever work. It does not mean that like ASLR works like this in the real life. It's just like the premise that all the code segments have to end with like 4 bytes, 2 bytes of zeros.
Because of the first like direction of B, right? If that first paragraph is omitted, then like if they just give us the output of the 3, we can't really assume.
Yeah.
It's like- it's like coincidence.
Yeah, exactly. Exactly. They might be just coincidentally the same. Yeah, completely correct. Yes, another question? Oh, stack canary being overridden like with like 32 bits? Yes, yes, yes. So the question is, why do we add like 2 to the 32, like another like factor of like 2 to the 32? And the reason we are doing it is if stack canaries are enabled, then what operating system is gonna do is it's gonna go over like your code. It's gonna check if the canary is the same, and if it's not the same, then we're gonna error out and we're not gonna continue executing any more code. That's all it says. Now, if the stack canaries are enabled, so our stack is modified to be like this. Recall that operating system will only let us execute the code if the canary is exactly the same. We're overriding it with bytes A. And the only time this will go through is if by some magical chance, the operating system chose the stack canary to be A. And this takes 1 over 2 to the 32. Because think of like garbage bytes as the hex like 41, hex 41, hex 41, and hex 41. Each of these is 1 byte, 1 byte, 1 byte, 1 byte, 1 byte, 8 bits, 8 bits, 8 bits, 8 bits. And so combining them together, we have like 32 bits that we need to exactly match together. That's why we're adding the 2 to the 32 factor to the solution. And 2 to the 16 comes from overriding the most significant bytes of the RIP. Does it make sense? Okay, perfect. Now moving forward, suppose that ASLR, stack canaries, and non-executable pages are now enabled, and no other memory safety defenses are enabled. Assume that the stack canary is 4 completely random bytes and no null byte. And now consider the same like following exploit, 16 bytes of garbage, same RIP, same shellcode. And what is the approximate probability now that the above exploit will work on any given execution of the program? And I'll give you guys, again, 2 minutes to think about it.
I have a question.
Yeah.
For non-executable pages.
Yeah.
We know that we will not be allowed to mess with the RIP, right?
Right.
But how does the program itself knows what to execute, or like which part of the, I don't know, memory addresses or like pages is something it can execute versus something it can't execute, if it's practically no difference when you, like, between like the buffer that we're trying to override versus the execution that the program is trying to do itself.
Yeah, that's a great question. The reason is actually like a little bit like out of scope for this class, but the question was like, why, how does like the program know like what to execute and what not to execute, pretty much, right? So like, how does it like any different from, like in this case, executing like the shellcode or like overriding RIP with regards to like when non-executable pages are disabled. And the reason is on the operating system side is you control which areas are write-only and which areas are read-only. And what non-executable pages do is you have four segments of the memory, stack, heap, code, and data. And what they do is they say, data, heap, stack, you are gonna be write-only and you cannot be executed. Code is where all the instructions play and like where all the instructions are located, and only this is the code segment allowed to be executed, but you cannot write to the code segment. Yeah, so all it says is that this is executable and all of the others non-executable.
So regarding what's in scope for non-executable pages, we don't need to be able to tell the difference, right? We just need to know that we can't mess with the stack.
Yeah, pretty much. The question was, for like midterm purposes, do we need to know how it works? No, just like know that we cannot mess with anything besides the code. And even with the code, you cannot even write to it. So you're not allowed to execute anything. Yeah.
Your RIP here is pointing to something on the stack, right? The OS knows that. Like you're pointing to the variable on the stack to execute. And like he said, stack is not allowed to be executed. So your pointer is invalid. It's not allowed when an X is enabled. I hope that answers your question.
Yeah, another question?
Just a question. So does that mean if ASLR is enabled and non-executable pages are also enabled, within memory, the split between stack, heap, code, and data, is it jumbled up based on these individual pages or like individual segments, or is it fixed? Is that all?
Yeah, that's a great question. So the question is, if ASLR and non-executable pages are enabled, does ASLR affect, so is non-executable pages boundaries, are they fixed or are they not? So for example, in this case, say that we said that all code is executable, but what happens if now ASLR is enabled, so we're gonna rewrite, this is actually now data, and this is code segment. And so would, in this case, data segment be executable? And the answer is no. The non-executable pages are per segment. So they're not hard-coded checks for memory. They're just per page. Your operating system knows exactly where the segment is, and it's going to make sure that it's not allowed.
So that means that the properties belongs to the entire segment of memory due to allocation by ASLR.
Exactly, yes. And so I guess knowing that, does anybody know the answer to this question? Yes? Yes, the answer is 0, because we cannot, the RIP lives on the stack and we cannot execute the stack. Yeah, so now in the interest of time, suppose that ASLR is enabled and no other memory safety defenses are enabled. As before, you run GTB and discover that the address of buffer is the corresponding one. We have already seen it before. And consider the following exploit, the same exploit. Note that the canaries are not enabled. Yes. What is the approximate probability that the above exploit will cause malicious shellcode to execute on any given execution of the program? And in the interest of time, I'm going to give you guys 1.5 minutes to think about it. All right, does anybody want to try to attempt this question? Or knows the answer to it? Yes?
1/2 in the first place, 32.
Why is that the case?
Because we need to, our address, the entire address that we put there, all of the bits need to match.
Right, right. That's a totally like fair point. So, one question to you is, where does the buffer live? What segment does it live in? Stack, right? Oh, would it be living in the stack on this case? I'm sorry? Yes, it's outside the function, right? So where would it live then? I'm sorry? Yeah, it's gonna be living in the data segment. Yeah, because that's where all the global variables live. And note that they're in the data, you're not gonna have RIP. RIP is not gonna be living here. So the correct answer would be 0. And the reason is because we're trying to override the RIP with like this address, the buffer now is located in data. There's not gonna be any RIPs to overwrite. And that's why there's like, even with like perfect probability, this won't work.
Same goes for global variables, by the way. You mentioned static, and
Yeah.
static and global live in data. So if you have a global variable, it would not be placed on the stack. It would also be in the data, and same thing applies.
Yeah, exactly. And I guess the last question is, generally, if an exploit succeeds with the probability of 1/2 to the 20, an attacker might try the exploit to the 20 times until it succeeds. However, whether an attacker is willing to try to the 20 times depends on whether the code has a timeout after each failed attempt and whether the code is even worth attacking in the first place. So which security principle or example is most relevant to this situation? I'm gonna give you guys a minute to think about it. All right, in the interest of time, does anybody know the answer to this question? Jay, know your threat model? Yes, that would be correct. And this is because if we know that maybe an attacker is not worth, like if thinking about like an attacker's capabilities and motivations is related to knowing your threat model. One threat model like may allow an attacker to try to the 20 times, but another may not. And yeah, does anybody have any questions? Yeah.
I kind of felt like the buff being outside of the functions and being inside of the functions with every subpart before was kind of a gotcha moment.
Yeah.
Are there like, what is the rule of thumb for those gotcha moments? Just like we reread the code every time?
Yeah, I mean, probably if you see that the question is looking exactly the same like the previous one, but there's like one like small difference between them. Like in the previous like question, we saw that one part, this like buffer living like outside of the function. It just was exactly the same question, exactly the same exploit, but the only difference was that the buffer now lives outside. I just like make sure to spend your time like reading the question and make sure that you understand like what differences are there like as you like go along, because we're not trying to trick anybody. Yeah, so I would say just like spend your time. Yeah. And yeah, if anybody has any questions, like please come see me. But otherwise, we're gonna end our midterm review session. Thank you everybody for pulling up. And yeah, good luck on your midterm. That's